Hello guys, welcome back to my channel, and today I'll be presenting on the topic single destination shortest path problem. Shortest path algorithms are one of the most important topics in graph theory and computer science. They help us find the most efficient route between locations, whether it is for navigation, networking, or delivery services. In this presentation, I'll explain what the single destination shortest path problem is, where it is used, the main algorithms that solves it, and the simple example to help understand how it works. So let's get started. Before we discuss the single destination shortest path problem, let's first understand what a shortest path problem is. A shortest path problem is about finding the path with the lowest total cost between nodes in a graph. The cost can represent different things depending on the application. For example, it could be the shortest distance, the least travel time, the lowest fuel consumption, or even the fastest internet connection. A graph is made up of vertices, also called nodes, and edges, which connect those nodes. Each edge may have a weight that represents the cost of traveling between two nodes. Shortest path problems are very important because they help systems make better decisions by finding the most efficient route. Now let's look at the single destination shortest path problem. This problem focuses on finding the shortest path from every node in the graph to one specific destination. This is different from the single source shortest path problem, where we start from one node and find the shortest path to every other node. For example, imagine a city with one hospital. Every road or intersection needs to know the fastest way to reach the hospital. Instead of calculating routes from the hospital outwards, we calculate how every location can reach the hospital in the shortest possible time. This makes the single destination approach very useful in many real world situations. It is used in many real life applications. One common example is navigation systems like Google Maps, Apple Maps, and Waze. These applications calculate the quickest route to your chosen destination. Emergency services also use these algorithms to help ambulance, police cars, and fire trucks to reach hospitals or emergency locations as quickly as possible. In computer networks, routers use shortest path algorithms to send data packets efficiently across the internet. Logistics companies such as Amazon, DHL, and food delivery services use these algorithms to optimize delivery routes and reduce travel time and fuel costs. Finally, robots and self driving vehicles use shortest path algorithms to navigate safely and efficiently. So, there are several algorithms that can solve shortest path problems, and the best one depends on the type of graph. The first is Dijkstra's algorithm. It works when all edge weights are positive or zero. It is one of the fastest and most widely used shortest path algorithms. The second is the Bellman-Ford algorithm. Unlike Dijkstra, it can also work with negative edge weights and can detect negative weight cycles. The third is breadth first search or BFS. This algorithm is used when all edges have the same weight, making the graph unweighted. Each of these algorithms has its own strength and is suitable for different situations. And now let's look at Dijkstra's algorithm in a little more detail. Dijkstra's algorithm calculates the shortest path in graphs where all edge weights are non-negative. For the single destination shortest path problem, we first traverse all the edges in the graph. Then we run Dijkstra's algorithm starting from the destination node. This allows us to find the shortest distance from every node to that destination. Some advantages of Dijkstra's algorithms are that it is very fast, produces accurate shortest paths, and works well on large graphs. However, one limitation is that it cannot correctly handle graphs with negative edge weights. Its time complexity is O of v plus e multiplied by log v, making it efficient for most practical applications. And the next one is the Bellman-Ford algorithm. Bellman-Ford is useful because it can work with graphs that contain negative edge weights. It repeatedly checks every edge to improve the shortest distance, until no shorter path can be found. Another important feature is that it can detect negative weight cycles, which are loops where the total weight becomes negative. The downside is that Bellman-Ford is slower than Dijkstra's algorithm. The last one is breadth first search or BFS. BFS is designed for unweighted graphs where every edge has the same cost. Instead of considering edge weights, BFS explores the graph level by level. It is simple, easy to implement, and very efficient. Its time complexity is O of V plus E. So, how do we decide which algorithm to use? If the graph is unweighted, then BFS is the best choice because it's simple and very fast. If all edge weights are positive, Dijkstra's algorithm is usually the best option because it provides fast and accurate results. If the graph contains negative edge weights or if we need to detect negative cycles, then Bellman-Ford is the better choice. As shown in the table, BFS has a time complexity of O of V plus E. Dijkstra's algorithm has O of V plus E multiplied by log V, and Bellman-Ford has O of V times E. Choosing the right algorithm helps improve both efficiency and performance. So let's look at a simple example. In this graph, our starting node is A and our destination node is E. Each line between the nodes has a number that represents the cost of traveling along that edge. For example, moving from A to B has a cost of 2, while moving from B to C has a cost of 1. If we want to find the shortest path from node A to E, one possible route is A to C, C to E, but its total cost is 6. Another route is A to B, B to D, and D to E. The total cost of the total cost comes to 2 plus 1 plus 3, which is equal to 6. The better route is A to B, then B to C, and finally C to E. The total cost is 2 plus 1, which equals 4. Because 4 is smaller than 6, this becomes the shortest path. Similarly, we can calculate the shortest distance from every other node to E node, which is shown in the graph. So let's look at a simple example. In this graph, our starting node is A and our destination node is E. Each line between the nodes has a number that represents the cost of traveling along that edge. For example, moving from A to B has a cost of 2, while moving from B to C has a cost of 1. If we want to find the shortest path from node A to E, one possible route is A to C, C to E, but its total cost is 6. Another route is A to B, B to D, and D to E. The total cost comes to 2 plus 1 plus 3, which is equal to 6. The better route is A to B, then B to C, and finally C to E. The total cost is 2 plus 1, which equals 4. Because 4 is smaller than 6, this becomes the shortest path. Similarly, we can calculate the shortest distance from every other node to E node, which is shown in the graph. To conclude, the single destination shortest path problem is an important graph problem that finds the shortest path from every node to one destination. We discussed its definition, several real-world applications, and the three main algorithms used to solve it. BFS is best for unweighted graphs, Dijkstra's algorithm is ideal for graphs with positive edge weights, and Bellman-Ford is useful when negative edge weights are present. These algorithms are widely used in navigation systems, computer networks, logistics, robotics, and many other fields because they help find the most efficient routes. So it's the end of it. Thank you for watching, and I hope this video helped you understand the single destination shortest path problem. And I'll see you guys in the next video.